Hi everyone, welcome back to the BGP Masterclass. In the previous episodes, we established a peering session and learned how to troubleshoot basic connectivity states. Today, we talk about identity. Every BGP router needs a unique identifier called the Router-ID. It looks like an IP address, but it's actually a name. Today, we will answer two questions. How does the router choose this ID automatically if we don't configure it? What happens when two routers have the same ID? Spoiler, it explodes. The rules for choosing a router ID are strict. BGP checks them in this order: manual configuration, BGP Router-ID X.X.X.X. This always wins. Highest loopback. IP. If no manual config, it picks the highest loopback IP. Highest physical IP. If no loopbacks, it picks the highest active physical IP. We currently have a manual configuration. We are going to remove it and force the router to use the automatic election. Let's jump to router 1. Currently, our ID is 1.1.1.1. I want to prove that BGP prefers the highest loopback. So let's create a new loopback with a massive IP address. Now we have 1.1.1.1 and 99.99.99.99. When we remove the manual command, BGP should switch to 99.99.99.99. Let's do it. Now, let's immediately check the summary. Look at the output. BGP router identifier 99.99.99.99. It changed immediately, and look at the up-down timer. This proves an important point. Changing or removing the router ID causes the BGP session to reset. The router realized, hey, I am not 1.1.1.1 anymore. So it tore down the connection and re-established it as 99.99.99.99. So we are now 99.99.99.99. But here is a trick. What if I add an even higher IP now? Will it reset again? We added 150.1.1.1. Let's check BGP. It still says 99.99.99.99. Why? Because BGP prefers stability. If the process is already running and happy with the dynamic ID, it won't restart just because a new interface appeared. To force it to see the 150 address, we would need to manually reset the process. Clear IP BGP asterisk. Now, let's see what happens if we have no loopbacks. This is the least preferred method. Let's delete all loopbacks. Now, R1 only has physical interfaces, IPs starting with 10.x.x.x. Let's reset BGP to force a new election. Now the router ID is 10.1.255.1, or your highest physical IP. BGP scanned the physical interfaces and picked the highest one. This is dangerous. If this physical link goes down, cable cut, the router ID disappears and BGP resets again. That is why we never rely on physical interfaces for router ID. We have proven that relying on auto-election is messy. If you remove a command, it resets. If a physical link dies, it might reset. It is unpredictable. But there is something worse than an unstable ID. It's a duplicate ID. In the next part, we will configure R1 and R5 to have the exact same ID and watch the session destroy itself. Okay, we had our fun with the automatic election. We proved that if we rely on physical interfaces, our router ID can change unpredictably if a link goes down. That is unacceptable in a stable network. So, before we break things again, let's restore the best practice configuration on router 1. We will recreate our loopback 0 and hardcode the router ID. I will also clear the session one last time to make sure this ID is applied. Now, R1 is stable. It is identified as 1.1.1.1. Our neighbor R5, the ISP, is identified as 5.5.5.5. Everyone is happy. Now, here is the million-dollar question. What happens if two routers claim to be the same person? In OSPF, duplicate router IDs are bad, but sometimes the network keeps working, with a lot of complaining in the logs. In BGP, the router ID is sent inside the open message, the very first packet of the handshake. The rule is simple. If I receive an open message with a router ID that is equal to my own router ID, I must reject it. Let's test this. R1 is 1.1.1.1. Let's go to R5 and force it to also be 1.1.1.1. Currently, R5 is using 5.5.5.5. Let's change it to match R1. Now, we need to reset the session for this new ID to take effect in the open message. Watch the console on closely. The session will try to come up, they will exchange hellos, and then, there it is. The session is dead. It cannot establish. Let's decode what happened. R1 sent an open message saying, "Hi, I am 1.1.1.1. R5 sent an open message saying, "Hi, I am 1.1.1.1. R1 received it and said, "Wait a minute, I am 1.1.1.1. You cannot be me." R1 sent a notification message and closed the TCP connection. This protection mechanism is critical. If BGP allowed duplicate IDs, the loop prevention mechanisms, which we will study later, would fail, and the network would implode. This leads us to an important realization. The router ID is not just a cosmetic name. It is used for loop prevention, especially in route reflectors. Path selection. If you have two identical paths to the same destination, BGP uses the lowest router ID as the final tiebreaker to decide which path to choose. If IDs are not unique, the math stops working. That is why the protocol is so strict about it. We cannot leave our ISP broken. Let's fix R5. And reset the session. Check R1 summary, and we are back to established. Peace is restored. To summarize episode 4, always configure BGP Router-ID manually. Do not rely on auto-election. Auto-election hierarchy. Highest loopback greater than highest physical interface. Uniqueness. Duplicate router IDs will kill the BGP session immediately with a bad BGP identifier notification. Your homework. Try to reproduce the auto-election lab. Create 5 loopbacks with random IPs. Remove the manual ID, clear the session, and guess which one BGP will pick. Verify if you were right. In the next episode, we are finally going to move beyond single links. We will look at eBGP Multihop. What happens when your neighbor is not directly connected? How do we peer with a loopback address? Thanks for watching, and see you in episode 5.